But anyways, all right, guys. Good morning. Make sure that you check in iClicker because a lot of you guys keep messaging me saying that you forget to do it. So check in right now. There's gonna be a few questions. Hopefully it works. I think it does. Let's see. Yeah, so I can see it. You guys are able to check in. All right, so I'm gonna go over today a review of some of the stuff that you've learned. I get that a lot of you are confused about the computer architecture stuff. So I stayed up last night till like 3 a.m. making these slides. So if I'm like kind of tired, that's why. But yeah, I'm gonna start from the beginning. He's been talking a lot about physical implementation of how to make a processor, but I think it's a little bit confusing. We need to take a step back. All right. So I want to first talk about what we mean by architecture and with an example of designing a car. Okay. So there's three different steps to like actually designing something. There's firstly figuring out the specifications of what you want to design. So for a car, we know that it has to have four wheels. We know that they have to have steering systems and power sources, etc. This is common for all cars, right? Um, you can use a car without understanding what's inside of it, which is good. So that's the highest level of description, just saying what does it do. The lower level, which is like actually physically implementing that stuff, is the microarchitecture, which is like actually specifying like the details of how it works, right? So every car drives, but then how does it drive, right? Um, so it could either be automatic, manual, or whatever. The realization, that's actually like physically putting it together. So maybe in a factory, what materials are you going to use? And there's an issue with this type of design is that you can create a car without knowing exactly how it's going to be used, right? You just design it knowing it will drive, but you don't know if it's going to be used for long distance drive, short distance drive. You just have to design it to the best of your ability. All right, but we want to be able to design something um, that talks together and try and connect these two problems. You know, the fact that you can use a car without understanding the internals, and you can design one without knowing exactly how people will use it. So again, architecture. There's a car. Just a picture I found on my phone of my car. Blueprint. Um, that's the micro architecture, and then the realization is actually building it. So understanding this design a computer. All right, so what is the architecture of the computer? Basically, what does it do? Right? You know that every computer wants to compute things, probably adding stuff, subtracting. You want it to do as many things as possible. So you'll see a lot of people talk about like general purpose computers. The architecture is basically just it can do a lot of computation. The microarchitecture is more of the stuff that you guys have been doing in the labs. So like designing the actual hardware for those computers, as well as writing instructions for them, which is what you're doing now in Lab 6. And then the realization is just how you actually physically implement that. So architecture, what does it do? You guys have talked about a couple different architectures, but I'll review them again. The microarchitecture, what specific instructions are you using? So you've probably heard of x86, ARM, RISC. These are different ways of describing how a computer works. But again, they all do the same thing. They just do it differently, have different hardware, etc. And then the realization, how do they actually build that? Right. And so we want to focus on the architecture and microarchitecture layer. How do we connect that? And we'll get into discussing the instruction set architecture stuff, which is the thing that bridges the gap between these two. So just as a recap, I think he's already talked about it before, but the most common type of architecture that people use nowadays and that the computers that you guys are using, your laptops, your iPads, whatever, they use the von Neumann architecture. So von Neumann, Hungarian-American scientist, he was the first person to design this general purpose type of computing machine, actually physically implement it. And all it says is that all the instructions, as well as all the data that you'll ever need for your program is located in memory. So, for your computers, all of that stuff is located in the RAM. So you always hear about wanting more RAM on your computer. It's so that you can fit more programs, fit more data, and it's the most flexible method of computing. But the main steps is that everything just runs one at a time. So there's a program counter. If you see at the bottom here, it just tells you go to this address in the memory and pull out whatever's in there and run whatever instructions in there. But there's also data located in there. So if you want to retrieve data from another place, you'd specify, I want to go to this address, and then it will pull things out. So I have an example that I found. Let me see. I have an example of a thing that I found that kind of shows like a good idea of like what's happening. So if I can load in these example programs and you can see like how the instructions are stored in memory. It's not really important to understand like how this is implemented, but it's more important to understand just the process, right? So you see here in the RAM or the memory, you have instructions, which is what we just talked about, as well as you have data. So you have numbers and stuff that you're going to use for your program. So this program specifically, it has there's a while loop. So you need to have certain things stored in memory, like this 5. When do we stop looping? And you also have to have values like this, like A, it needs to be stored in memory somewhere so that you can keep track of it. Right, because we don't use registers for everything. Registers are usually used for computation in between steps, but you're not really using that for data storage. So if I step through this, you can actually see how the instruction gets pulled from the memory, and if you did lab 6 already, then you'll recognize that we ask you to make instructions and have them like correspond with a certain binary. This example, if I change it to binary, you can see that that instruction is just a sequence of numbers, just like you guys have done. And so on the first step, it pulls it in and says, here's the instruction I want to go to, or here's the instruction that I want to do. And what does that instruction say? So it says I want to load a register with some value from memory. So again, we said that data is also stored in memory. So what this is going to do is it's going to look at address 15, which is this one, and it's going to load it into this register. So you see that. So it loads in a 0. Okay. So yes. Are they located in the same block? I mean, they can be. That's just up to you to design it. Usually the processor will separate those things into different chunks of memory. So it'll take this overall space, split it up into different places that you should put data stuff and program stuff. But, for a very simple processor, it doesn't have to. I mean, memory is memory. It all does the same thing, right? Yeah, I mean, it could be. But again, this is just like a very simple example, just showing like how things come from memory. But yeah, when they're actually when you're actually designing something, and what you'll do in Lab 7 is you'll use a processor that specifies, what sections can be used for what. All right. So that's just to show you, instructions and data all in the same spot. All right. Are there any questions about the von Neumann architecture at all? Hopefully you've already seen this, so I don't have to talk too much about it. All right. So let's get into the actual instruction set architecture stuff, which is much more interesting. It's getting more into the software stuff, which I know that some of you don't like, but some of you do. So I mean, this is the key of computer architecture. So the instruction set architecture bridges the gap between hardware and software. All right. So far you've designed a computer, like a very simple computer, of course, but you've designed a computer in VHDL with your BDFs and stuff, and you can manually load in instructions using the switches on the D10, which is great. But you're always having to look, you have to write down like load, and you have to see which, bits does that mean. You usually have a table saying like load is instruction 0, move is instruction 1, etc. The instruction set architecture basically is that, right? So it just defines all of that stuff in a nice table, easy to use. And yeah, so it goes right above this level, but it's kind of like a hardware software thing. It's basically saying these sequence of bits correspond with this instruction. All right. So as I said, they define what type of instructions exist on a processor. So the processor you design, I think, has only 3 bits for instructions. So there can only be 9 instructions in total, I think, for the Lab 6 one. But again, most processors that you guys are using now, like the x86 Intel chip, or the ARM or the Mac processors. Those things have a lot more instructions. But basically, they define an interface that any program can, so that any program can run on any chip that follows the same ISA. So x86 was invented in like 1978, which was a long time ago. It was a 16-bit processor. However, it has the same instruction set architecture as we have now. Obviously, the processor has gotten bigger, so a lot of those core instructions that were there before, they can still be run now. So the one of the design factors that you want to keep into consideration is how long can this instruction set architecture be used. You basically want to have future compatibility over trying to optimize how fast things go. And that's one of the key things in general purpose computing. When you start to do like application specific hardware design, that is kind of a different approach. You want to design the fastest circuit to do your specific application, but that's obviously much more expensive. When we're designing computing machines, usually we want it to be as flexible as possible so that we can do as many things as we want with it. Von Neumann architecture, again, as I said, has been the most dominant one over forever, basically. But there's also another architecture called the Harvard architecture, where it separates program and data memory. And it's a little bit faster. So there's certain downsides to using the von Neumann architecture. But again, it has less flexibility. So there's a trade-off between speed and flexibility. We usually want that flexibility for our machines. So that's usually what we go for, even though there are some downsides. Every instruction set architecture defines different instructions that are atomic, meaning they do one single thing usually. They're sequential, so they should go in order. And I think I wrote in order instructions. Basically, when someone writes a program, they should expect that it goes one by one. Even if the processor does some tricks to do things at the same time, you might hear like multi-core CPU stuff. Even if they have that, it should still appear to them that everything happens in order. All right, and that's very important. There's a couple different philosophies about ISAs. There's the reduced instruction set computers, which try and make smaller instructions that do less complicated things. So you can imagine if you want to do the same program with small instructions, you might have to have a lot of instructions to achieve the same goal as having much more complex instructions, which is what the CISC, the complex instruction set computers do. However, even though you're using less instructions, each of those smaller instructions uses significantly less power because you have less hardware to run at the same time. And so there's a trade-off of your program gets bigger, but you're using less power. And that's like what the ARM chips do. Those Mac M series, they use the RISC architecture, as well as the MIPS, the one that you guys are going to be learning about. But if you guys are using Intel chips on your Windows machines, those are complex ones, so they use very big instructions, and the hardware is much more complex, so you can achieve much more with less instructions, but they use more power. All right. Are there any questions so far about what it, yeah. It just depends on the implementation. So usually if you were trying to implement the like complex instructions with the same amount of hardware as you were for like a reduced instruction set stuff, it'll probably take longer to do the complex one. But again, usually people that design complex instruction set architecture processors, they accordingly add much more hardware to achieve those much more complex instructions, right? So I mean, the timing I don't really know specifically, but that's generally the trade-off. Generally, is just like yes, those instructions go faster in the RISC, but there's just going to be more of them. But at least they take less power, right? But it's starting to become much more dominant now. I mean, we hear a lot about ARM chips and those Mac chips. They use very little power, and it's really important in laptops. Power consumption and data centers, especially because they're like drawing so much power beyond belief. So they need to get the most power efficient stuff, right? So they're willing to take that trade off for that. All right, so I'm going to do a quiz really quickly on iClicker. Basically, what is the main purpose of the instruction set architecture? Should be very easy, but I just need to make sure that you guys are doing it. All right. So one, to define the physical layout of the transistors. Huh? No, there's not 10 iClicker. There's 3 iClicker questions. Again, I made this at 3 a.m., so I don't even remember what I put in here. I only slept like 4 hours to be honest. But that's how it goes. I have classes too. I had an 8:30 this morning. That wasn't very fun. I'll give you like a minute and a half, so you have 1 more minute. Should be super easy. So the second one is to describe how software communicates with hardware, defining the instructions in the visible state. So what's in the memory at this current time. C, to specify the manufacturing process. I mean, probably not. And then D, to describe the hardware design at the register transfer level, something that you've been doing now. All right. I don't know how many people are inside here right now, so I have to check. Okay, there's 125 people here. So I'll wait 20 more seconds and then we'll continue. And I'm sure that if some of you guys are in a computer organization, then this is the same stuff that you've already learned. But the cool part about this class is that you get to build the processor that you're writing instructions for. Comp org, you don't do any of that. Honestly, it's very boring. So that's just the theory, right? Huh? Yeah. All right. Let's keep going. All right. Whoever clicked D, I think you need to. All right. I'm not going to say anything. All right. So, this define when we actually design instructions, they can be literally anything, right? In lab 6, we literally just made up some random processor to give you that has random instructions that does random stuff. Um, but usually there's more thought put into it, but they have like specific goals, right? You want your processor to do the most possible things, be the most flexible, right? So we want to give it as many instructions as we can that can do the most possible things without us having to buy special hardware. Right now you hear a lot about buying GPUs and stuff. That's a specialized piece of hardware to do something that a processor can't do quickly enough, right? But in general, we want to design it such that it is the most flexible for every application. So one of the main things is that every instruction in an ISA has the same amount of space to be used. So for example, if we define if we have a processor that has only 16, that's called a 16-bit processor, that means that every instruction has to be 16 bits, no matter what type of instruction it is, whether it's a load from a register, load to a register, add numbers, I guess jump around in the program memory. They all have the same amount of space to work with, but they all need different types of data to actually operate. Like loading from a register, you need to specify the instruction, the register you want to load from, and the thing that you want to load into it. But if you wanted to add numbers to a register, for example, you might have to do something different. Or if you wanted to go somewhere else in memory, you would just say, my instruction is I want to jump to this place, and then you provide that instruction, right? So every type of thing that you want to do has to have different types of information. So there's different types of instructions to correspond for that. They basically use that same amount of space that you have for an instruction and then use it in different ways. So again, the design is trying to fit what's needed, but without wasting extra space. And I'll get into like the different formats here. So you can see an example with the MIPS ISA. Again, if you don't know what MIPS is, it's the multi-processor without interlocking pipelining stages. Basically, it's a super simple processor designed for education. Probably heard of it before. But it's very simple. There's only 3 different types of instructions. So every instruction has the same amount of size the same amount of bits that can be used. But we need to do different things, right? We need to load from registers. So that's called an R-type instruction. There's the I-type instruction, which is when we want to do something with immediate values. Like let's say we want to add a register with a 5. Well, we don't have that. We don't just have a 5 laying around in memory. We just want to add it directly. So instead of providing the 2 registers that you want to load stuff to, the I-type, you provide that 5 inside of the immediate part of the instruction. But you see that just based on this, the R type and I type have significantly different needs, right? So we have to map it differently. The jump type, which is I guess the J type, there's only two instructions in the ISA that use this, but basically you just specify this is a jump instruction, and then every other bit, so all the other 32 minus 6 bits, you are going to be using to just specify, I want to go here, right? So this is how we get that flexibility in a processor. We just map the amount of bits that we have for an instruction into these different types, and now we get a lot of flexibility. Yeah. SB. Oh, I think I can't remember. It's, honestly, I remember I was reading a book last night about MIPS, and I like got a table of examples, but then I forgot what it was. I put it in there for a reason. Oh yeah, okay. Store. It corresponds with store byte. So basically, take a value from a register, okay, and then put it into memory. So the R types, they only use registers. They don't even need to access the ALU, right? The I types, they probably need to access the ALU because they need to do add operations, subtract, right? And they also need to store stuff to memory. I think branching is also looped in with that. Yeah. Well, if you're just, yeah, I guess if you're trying to add two values from a register, then yeah, it would. But if you're doing instructions like load, for example, I guess it wouldn't need to. Um, yeah, I mean, yeah, you're right. Okay. And then the jump type, again, there's only one instruction that does that. Yeah. I don't remember specifically what it maps to. Let me see. To be honest, I don't even remember what this sham T stands for. Let's see. Yeah, so there's like this big table with the instruction set that explains what it is, but I don't remember. So I'm just trying to highlight the fact that we try to use the, same amount of bits that we've got to do different types of things. So I'm sorry, I don't remember. So so I'm just giving this as an example, but every CPU is designed differently. Like the one that you guys are doing now, you designed it yourself. It's not going to look like this, but it's still everything will follow like the same sets or steps of instruction. So the first step is the instruction fetch. So basically, find the instruction in memory, or yeah, find the instruction in memory, and then we need to decode it. So if you remember in Lab 6, you have to take the instruction and then say, oh, I want all these multiplexers to be this and that. I want the opcode to be that based on whatever's in the instruction. And then there's the execute. So actually do the operation. So if it's like an add operation, do it. Of course, it's combinational logic, so it happens instantly. But we're still separating it into stages for good reason that you'll find out later. There's also the memory access step. This is only necessary in in the MIPS ISA. This is only necessary for memory access instructions, like those. I think they're the I type, right? So the I type instructions, they require memory access. So those are the only ones that are actually going to use that. But that's there if it's needed, and then write back. So if we actually have to, you know, send something back to our data space, our registers, then we'll do that at the last step. And then the stuff at the top, you see, there's some incrementing happening. We'll talk about it in a second. Are there any questions about this? This is just, again, a general layout of how a CPU might look, but it's not representative of every CPU. But for a von Neumann architecture, this is kind of the steps that you would follow. And it's the same steps that you guys are designing in the lab. So you've probably seen like this super complex stuff. I'm not really gonna go into detail about how to design it. If you take digital design, this is the final project is to build this whole processor by yourself, fully in VHDL. So if you take digital design, have fun. Honestly, I TA'd for that class last semester. I did not do this project when I took the class, and it was very hard for me to understand because I hadn't done it. But if you guys are doing the CPU design that you're doing now in Lab 6 and you actually get it done, I think you'll have a much better time. All right, because I didn't learn how to do this until after I took digital design. So we're trying to implement it now so that you guys know how to design something basic. And then once you know that, it's very easy to transfer those skills up. Um, so I think the controller that you built in Lab 6 or that you're building in Lab 6 is super simple. It basically just says, here's the instruction. I think you have to wait in a ready state. And once the instruction is ready to go, it just says, okay, if it's this instruction, send out these select signals to the multiplexers, and that's it. And that's pretty easy. But of course, when you have more instructions, so you've got more than 9 instructions that you've got in the lab, you're gonna have to do a lot more control logic to achieve that stuff. So like the branching and the jumping. So just to summarize, the steps that every single cycle processor follows is that 5-step thing that I talked about before. All of these steps happen within the same clock cycle. Okay, so we're visually dividing it into pieces that are easy to understand for us, but again, they all happen at the same time unless you use a multi-cycle processor. So the MIPS by itself is just designed like this, where one clock cycle happens and this all happens. And I can show you a diagram of what that means. So at the top, we have the single cycle implementation. Every instruction takes one full clock cycle to do all of those steps, right? And so certain instructions might not need to use all the hardware. Like, for example, memory instructions, they need to use the memory access. Then other stuff might not need that, right? Just loading to a register, that's probably pretty fast. So the downside of doing single cycle implementation like this is that the clock cycle that you use for your processor has to be pretty long, right? It has to at least accommodate the instruction that takes the longest time. So you see, load word takes a pretty long time to execute on our single cycle processor, but store word doesn't, right? So it doesn't take that long, but then you see the gray area on the right. Basically, all of that other time is wasted, right? Because we have to make sure, because we can't change the clock cycle for every instruction, right? That's a constant value. With the multi-cycle implementation, we split up all of those stages, those logical stages that we talked about, into steps. And the way that you do that is you put a register between every single step, just logically. And that makes it so that every clock cycle, only one of those steps can happen at once, right? Because otherwise it all happens at the same time. And yeah, I'll show you a diagram of what that means. But first of all, are there any questions about this at all? All right. And that stuff that you saw at the top of the MIPS diagram with the incrementing stuff, with the MIPS ISA, since it's 32 bits, that's 4 bytes, right? Because every byte is 8 bits. You've got 4 of those. We need to store that in memory. The memory is not 32 bits wide. So it's not like you say, I want to go to address 0 and it spits out, it doesn't just spit out like a 32-bit value, which would be pretty easy, but obviously that's just not how it's designed. So, but we still need 32 bits for our instructions. So what we do is we just say, the the first part of the instruction is at this bottom address, but that's only a quarter of the instruction, right? So we need to take this value, this value, this value, this value, and stick it all together, and that gives us our full 32-bit instruction. And so you see every instruction, since it takes 4 bytes of information, what I would do first is for my first instruction, is read all of this stuff, all 4 of these bytes, execute the instruction. And then since the program counter starts at 0, we read all 4 of these because we need 4 bytes. And then instead of incrementing it by 1, we're not going to the next address like this. We're actually going up here because our next instruction is the next 4 bytes. Right. So that's why you'll see that +4 on the diagram, which is, let's see. Let me go back. Yeah, so you see there's a +4. So you're adding 4 every time rather than adding 1, which is what you're doing right now for lab 6. All right. So there's going to be another question here. Let me pull it up. All right. So how many core stages are there in the MIPS ISA? Really, most of them do the same thing, but how many did I discuss? There's the starting instruction fetch, decode. There's a few more. There you go. Sorry, I forgot to pull it out here. All right, I'll give you 1 minute. So fetch, decode, execute. That's three. All right, I'll give you 15 more seconds. So lock in your answer. All right. All right, we're gonna finish up. All right. Five. Okay. Fetch, decode, execute, memory, write back. Okay. So for those of you who put four, we have five stages always for this specific one. But again, you might find that there are different amounts of stages in a different processor. But typically, you'll see stuff that looks like this. You'll almost always see fetch, decode, execute, heard when you learn about any processor. But they might do some extra stuff. So five is the right answer. Three is not. Four is not. Six is not. All right. Bless you. All right. So who likes programming? Anybody? CS majors in here? Are there actually any CS majors? Okay, I don't know why you take this class. This is like this is basically what you're going to do in microprocessor applications. So I know some of you hear about that class. It's all assembly. There's no hardware design. There's nothing. It's just you have a processor. Here's the instructions. Do something. All right. So we want to get you started early with this stuff by teaching you. You designed a super simple processor. You need to write some instructions to achieve some functionality. When you get into microprocessors, they'll give you an 8-bit processor. We gave you a 3-bit processor, very small, but you're going to get an 8-bit processor, which is still very small compared to what modern computers use now. You probably hear 32-bit or 64-bit. The instructions are literally 64 bits long, right? So that's a lot of instructions. But yeah, we want to get you started early so you kind of have an idea of what you're actually trying to do. So he doesn't let you write in C or Python or whatever you guys are used to. You have to, instead of writing in C, you have to write at the lowest level and say, I want to, do those atomic steps to achieve a very complex thing. And eventually you get to do C at the end. But you definitely don't start out like that. And that's what a lot of people struggle with. All it is though, is just taking, steps and translating it into those atomic things that we talked about before to achieve something bigger. This is a super simple example of some C code. Each one of these things can be done in one assembly instruction. So the first one, we're instantiating a variable A, and we want to load a value of 5 into it, right? That's very easy to understand. So let's say that we have an instruction called LDI, load immediate, and let's just say that register 0 is going to represent our variable A, 5 is our immediate value that we want to store in it. Okay, and it doesn't matter. You might have a processor that has different instructions, but you have to find the one that matches the functionality that you want to achieve. So for B, we load R1 with 10. Let's just say R1 is B. C, we want to add 2 registers now, right? So don't think about variables, but think about the registers representing those variables. We want to add A and B together. We said that R0 is A, R1 is B. So let's say that we have an instruction that can add 2 registers together. Usually it'll be in a format like this where you say, I want the addition to be stored here, but then I want to add these 2 registers together. The next instruction, B equals A plus B. Again, same thing. We want to overwrite B with the added value of A plus B. And then the last instruction, add immediate. We're just adding 5 to whatever's inside of C. So if you really think about what the hardware is doing, you're just taking the registered value of C, passing it through the ALU with an immediate value of 5, and then storing it back into C. Yeah. The data type. So when you actually work with memory, I mean, memory is they're just bits. Okay. So usually when we write the data type here, we're just saying what we expect to be in there. But every single thing that's stored in memory is just like a sequence of bits. Okay. So um, in this case, it doesn't really matter. Let's say that my processor can only do arithmetic stuff. So I can have integers stored inside of those registers. But again, usually what these symbols correspond to is just how much space in a register do I need, or how many registers do I need to store this value, right? Usually int is like, they usually say that int is like 4 bytes or something, but it just tells your compiler like how much space do I need to store this value. All right. I'm not going to actually do any assembly programming because I don't really want to do it right now, but you will do that in homework 7 and lab 7. So it's going to come out very soon. Are there any questions about any of this? I'm just giving you a taste of the hell that will be microprocessors, I guess, or whatever people say about that class. I took that class and it wasn't that bad, but. No. Mhm. Yeah, I have some examples at the end. I'll show you what the actual hardware looks like for that multi-cycle implementation. But yeah, you're right. I didn't know if I was going to get into it or not. But there you go. Okay, great timing, guys. So who has learned about planning already? Comp.org? Yeah. Okay, that's good. Okay, well, for those of you who aren't familiar with pipelining, I swear that this example is in every single class, every single book I've ever read. So I actually have the book for this class, and I just like I just scanned it. So you'll see this everywhere, but it's a really good example, right? It makes it really clear what's going on. So what we were talking about before, where everything happens at once, you know, it sounds fine until you get to like computers that we have now. They have to do so much stuff, right? They have to run so many different applications at the same time. We need to go faster. All right. Simply put, we have to go faster. We're trying to make our general purpose computer much quicker. But remember that trade-off with using general purpose stuff versus the Harvard architecture is that it's going to be slower. So you have this trade-off of it's slower, but it's more flexible. So what are the tricks that we can use to make it more, more execute faster or do things quicker? So pipelining is one of those things. So if you think of this example here, imagine you're doing your laundry, your laundry machine, you've got your dryer, and you have to do these other steps of what are, oh, I don't know what the blue thing is. I guess folding up your clothes, right? And then putting it away. So imagine you were to do your laundry process by putting stuff in the washing machine. You just wait for that to finish, and then you put stuff in the dryer once the washing machine's finished. But that's it. You've still got dirty clothes waiting around, but you just don't touch the washing machine. You fold your clothes, you put them away, and only then do you actually start doing the next load. But of course, that's not what we do. Naturally, we're inclined to use all the resources that we have as often as possible, right? So pipelining is that process. So if you see in the diagram, at the top is that very inefficient method, which is what the CPUs that you guys are designing now do. But of course, clocks are pretty fast, so it doesn't really affect you now. But once things get bigger, it'll be a lot slower. Here's the pipelined way of doing stuff. So once the first load is done in the washer, you move it to the dryer, and then you start the second load in the washer, right? And then you keep doing that. So the amount of time it takes is significantly less. What you hear a lot is that people will say pipelining takes, it takes the whole length of I don't really know how to describe this, but you have to do one full cycle of the first one, and then every subsequent thing finishes one cycle after that first one. And you can really see that with this like staircase shape, right? So that's how you would calculate how many cycles a pipelined process needs to finish. But you see, instead of finishing at 2 a.m., we can finish before bedtime, hopefully, right? Are there any questions about this process? Hopefully it's clear, at least the intuition behind why we would want to implement this real world thing into our computer. All right. So if you remember what I said for this, specifically for this processor, but again, many other processors have their own design, and you can do this as well. We're able to separate our computer into different stages. All right. So there was the instruction fetch, decode, execute, memory, write back. We can separate those using what? What can we use to separate those stages between clock cycles? Yeah. So we can put registers between each logical step of our execution. And what this allows us to do is basically every clock cycle, instead of the whole thing happening at once, only one of these things will happen every single clock cycle. We can actually speed up the clock if you remember looking at that diagram. So if I pull up the next slide, it should show a picture. No, that's the wrong one. Yeah. So let's add a register in between there. So now we can really use all of the pieces of hardware we have. So for this first instruction, what will happen is the thing will be fetched. Great. The next cycle, it'll move to the next register, and then the next instruction is loaded simultaneously at the same time, so that the fetching happens at the same time as this decoding step happens, et cetera, et cetera. So that sounds good, right? We can do multiple things at once, but there's some dangers to doing this, right? Because certain instructions require the same pieces of hardware to run at the same time. You might need, I don't know, the ALU and the memory at the same time, but if we've got a register between each of them and we're doing one thing at one instruction in every single step, then we'll come into some conflict here. Right. So this is one of the dangers of pipelining. So we can't just like use it blindly without knowing what we're doing. Here's a better visual example of what pipelining looks like in the processor. So same thing as the laundry. The first instruction takes its whole length of time to finish, but then every subsequent instruction, since it just started one cycle behind the first one, finishes one cycle after the first one. Well, after the one before it. So at every given point, this is good so long as the ALU is only being used for this instruction in this step, the ALU is only being used for this instruction in this step, etc. But obviously what happens if two of these pieces of hardware are needed at the same time in the same clock cycle, right? So that's the danger. So CPU will blow up. So you'll learn about this in computer organization as well as computer architecture, the methods to solving these problems. There's many different ways that you can solve these, what they call data hazards, preventing your CPU from blowing up. I'm not really going to get into that too much, but that is something that you need to be aware of when you're actually doing pipelining. But if you can pipeline well and you make it very robust, your processor has become much quicker. All right. So that's a good thing. All right. So if you want to learn more about this stuff, then I would really suggest just searching up a free PDF of the book at the top here, which is the one that we have for this class. And that's where I basically learned everything about this topic. I honestly did not learn much from this class because I never listened in class, nor did I really go to class like some of you guys, I know. But I would say look at that if you're really interested in computer architecture, especially if you're a computer engineering student. It would be really important for you to understand this. We are trying to get you into this with homework 7, where we'll ask, or no, I think it's lab 7, where we'll give you a CPU, something more complex than what you built in lab 6. And we'll say, here's the instructions, here's the registers that you've got to work with. Now achieve this, do this equation, etc. So we'll give you that, but you're not getting the experience of actually designing those extra pieces of hardware because you've only designed like arithmetic operations, load operations. you can learn how to design the branching stuff, the jumping stuff. That stuff's all in that book there. And you can play around with this CPU that I found online, which really clearly shows what happens in a processor. This instruction set that this guy has made is only 3 stages: fetch, decode, execute. Only has 16 addresses for memory, very little amount of instructions that you can fit there. But it's really good for visualizing. So you can click through it and you can have it either single step showing the different stages, or you can set it up like this and then change the speed so you can watch, how a processor is doing something, which is really cool. You can even build this stuff in Logisim if you want. I know one of our other teaching assistants, he built the whole MIPS processor in Logisim. I don't know why he did that, to be honest. He was one of the students in digital design last semester. And that class will teach you how to design this stuff in VHDL, because obviously if you had to drag logic gates for every single one of these components, it would be terrible. All right. So that's why digital design is good, is that you can learn how to do this all in VHDL. And to be honest, like once you get good at it, you can design like these gigantic processors very quickly. Maybe not to the level of the Mac M series chips. Those are obviously much more complex, and I think one person can understand. All right, but you can do a lot with that. So, all right, that's about all I have for you guys. So, if you have any questions, I'm happy to answer. Thank you.